Alright, welcome back. I know you guys are exhausted, but still, there are several more topics that we have to cover in 5.2. We went through probability mass function and cumulative distribution function, and putting those two together, we call those probability distribution. And then we went through some examples of probability mass functions and cumulative distribution functions using earned models. We went through some conversion between mass function and cumulative distribution function. We went through expected value, variance, and standard deviation, and we studied some examples, some computation examples. Okay, for the computation, let's consider expected value and standard deviation of a certain random variable when a mass function is given. This is going to be easy. Why? Because all the x value and then the probability value, x value is probability, x value is probability. They're all given, so all you have to do is just multiply all those and add them up, and we get the expected value here. X value times the probability, x value times the probability, x value times the probability. Just add them all up and you get the expected value. How about the standard deviation or variance? We calculate deviation squared times the probability, add them all up. So here it is, deviation squared times the probability, deviation squared times the probability, deviation squared times the probability. Just add them all up, and that's going to be the variance. Square root of it will be the standard deviation. Okay, for mass function, it's pretty simple. What if we have a cumulative distribution function instead? How do we work this one out? Well, what I suggest is to convert it into a mass function. Find the mass function first, and then go from there. How do you find out the mass function? Look at the breaking point, breaking point, the breaking point, and breaking point, and each breaking point you have to get the new contribution. So far 0, it became 1/3, so difference is 1/3. So far 1/3, it became 1/2, so difference is 1/6. So far 1/2, it became 3/4, so the difference is 1/4. So far 1/4, and the accumulation is 1, so the difference is 1/4, kind of like that. And you get the mass function. Once you have the mass function, calculating the expected value is simple. Y value times the probability, y value times the probability, y value times the probability, and so on and so forth. Add them all up, and we get the expected value. How do we get the variance and standard deviation? Deviation squared times the probability, and then just go ahead. So 0.25 minus this expected value squared. So deviation squared times the probability. Deviation squared times the probability. Deviation squared times the probability, and so on and so forth. Calculate it all using handed calculator, and then take the square root, and then we get the standard deviation. Well, about 4 numbers you can use calculator, but if you have something like 10 such numbers, computing this kind of thing with calculator is more or less crazy, so I'm not going to write that kind of problem. There goes the mass function and distribution function. Now, we have some time left. Let's talk about, some advanced topics. The first advanced topic is the normalization theorem. And the result, you guys must remember. The proof, if you don't remember, that's okay. X is a random variable with expected value mu and standard deviation sigma. Then you can define a new random variable by this. X minus mu over sigma. Then the new standard deviation like this has a mean 0 and standard deviation 1. Sometimes people call it normalization, people call it standardization or something. I prefer the term normalization. Why is that? Well, here's the proof for expected value. You want to find out expected value of x minus mu over sigma, right? Okay, so this is the new value. X, the capital X can take value x1, x2, x3 all the way xn. So if you calculate x minus mu over sigma, you get x1 minus mu over sigma times the probability, and x2 minus mu over sigma times the probability, blah blah blah, all the way up to xn minus mu over sigma times the probability. And then we do some algebraic manipulation and factor sigma out, so we have 1 over sigma there, and then distribute in each p1 into their p2 there, everything. Then we have x1 p1 minus mu p1, x2 p2 minus mu p2, and so on and so forth. Now break up all these parentheses and then put all those pluses and minuses together, all the x's together here, x1 p1, x2 p2, everything, and then mu1 p1, mu p2, and so on here. And what do you get here? x1 p1 plus x2 p2, that is the expected value of x, so that's mu. How about the right hand side? Mu times p1 plus p2 plus all the way up to pn, do the sum of all the probabilities, so it is mu times 1. So what do you get? Sigma times mu minus mu, so that's 0. Expected value has to be 0. Phew. Interested students only. Variance will be even more challenging, kind of like this, variance of x minus mu over sigma. So this random variable will take x1 minus mu over sigma, x2 minus mu over sigma, and so on and so forth. So that value minus the expected value squared, that will be the deviation squared. But what was the expected value? We calculated as 0 in the previous problem. So we don't really have to do anything because subtraction by 0 will not change anything. So this is, as a matter of fact, equivalent to everything without minus zeros here. We're gonna get something like this. Okay, can we do some simplification here? Yes, we can take sigma squared out, so we have 1 over sigma squared. If you do that, we have only the numerator. x1 minus mu squared times p1, x2 minus mu squared times p2. What do you get? We have deviation squared times p1, deviation squared times p2, and so on and so forth. That's a variance. That's sigma squared. So what do you get? Sigma squared times 1 over sigma squared, that was there before. We have to have 1. Variance is 1. Take the square root of that 1, you get 1 as a sigma as well. The standard deviation is also 1. Okay, that was the normalization theorem. If you forget about the proof, well, that's okay. But do not forget about this formula, z equals x minus mu over sigma. This is going to come back and haunt you over and over again from chapter 6 and on, I think, all the way toward the end of the semester. Okay, we have sufficient time, so let's discuss further optional topic here. Properties of expected value invariance. If you multiply something to expected value, then that comes out. If you add something, well, addition is preserved. And variance, that's different. If you add something, that goes away. If you multiply something, a squared comes out. The first one is relatively easy to understand because variance is two-dimensional quantity. But why is adding something just disappear? That's because variance is measuring the deviation squared, and so on. But if you just parallel shift everything by b, then expected value is also shifted by b, so deviation stays the same. And a final property here, well, you can actually prove it rigorously. if you're interested in this kind of things, but I don't see any interest here, so I'll leave it as a optional topic to interested students. Another topic here, what is the relationship between expected value of this probability and the mean of the population? Well, okay, here's one way to see it. The mean of the population is this: add up all those possible values divided by total capital N. But then again, there gotta be some repetitions, and take those out, and then you can consider first parenthesis as x1 times f1, where f1 is frequency, and the next frequency, and so on. And this final parenthesis is xn times frequency fn. Now if I take all those x1, x2 those out, we get f1 over fn, f2 over fn, all the way up to fn over fn. And what are these ratios? Those are the probabilities. So what do we get? The mean of the population is the same as the expected value. We have really beautiful results between one and the other. Mean of the population is something we can never calculate directly, but we can track it down using the probability theory and expected value. Theoretically speaking, this is really striking. That is why the probability theory is really the backbone, theoretical backbone of statistics. You can find out everything about population using the probability. The same goes to the population standard deviation. For population, we don't divide it by n minus 1, we divide by just total n, and then we have the repetition of same thing a number of times, so you can replace this one by deviation squared times the frequency. Same thing goes for the next bunch, here's the last bunch. Deviation squared times the frequency, and do the same thing. Take the deviation squared out, and what do you get? f1 over n. The same thing, f2 over n, and so on. We have fn over n. And each ratio is the probability. So what do we get? We get the variance of the random variable. So what do we get? Variance of the population is the same as the the variance of the population is the same as the variance of the random variable. Again, very striking property. Same goes to standard deviation, because all that is left to take the square root of these two. In short, we can find out a lot, actually everything about the population, using the theory of probability. That is why the probability is important in statistics, at least theoretically. But then again, in 1000 level students usually are not that interested in the theory, so if you understood me, fine. If you didn't, that's okay. The latter half of this video was rather exceptional, and I'd regard those as optional. That concludes 5.2. Thank you.